We need to look at one more property of the cubic curve, and that is the point of inflection and concavity. Now, the point of inflection is defined as the point on the graph where the curve changes from concave up to concave down. What that means to us is, in other words, where the curve changes from a happy face to a sad face. Now, I've got the sketch of a curve below. And in this first section, highlighted in green, that portion of the graph has a happy face. In other words, that portion of the graph is concave up. And the next portion, highlighted in pink, is a sad face, and that portion is concave down. And that point where it changes from a green graph to a pink graph, that is known as the point of inflection. Now, in a graph that has two stationary points, the point of inflection will always lie exactly halfway between the two stationary points. So the stationary points on this curve are at 2 and minus 32 and 6 and 0. So exactly halfway between 2 and 6 is 4, and exactly halfway between minus 32 and 0 is minus 16. We need to be able to calculate that point of inflection though as well. And to do that, we are going to use the second derivative equal to 0. Now, the equation of the previous curve is defined as f of x is equal to minus x cubed plus 12x squared minus 36x. And the first derivative will then be minus 3x squared plus 24x minus 36. The second derivative is just the derivative of the first derivative. So it will be minus 6x plus 24. And if I make that equal to 0, I should be able to find the point of inflection. So we can take 24 over to the other side, divide by minus 6, and I get an x of 4. If I substitute that back into the original function, I will get the corresponding y value. So I can see that 4 and minus 16 is in fact the point of inflection. We need to learn about the second derivative test and how it can help us. We just need two reminders first. The stationary points always occur when the first derivative is 0, and the point of inflection occurs when the second derivative is 0. Now, if AB is a stationary point on my graph, with A being the x value and B being the y value, if the second derivative at A is positive, it tells us three things. First of all, the stationary point is a local minimum. So now I don't need to draw the graph anymore to figure out if it's a local minimum. If the second derivative at that point is positive, it's a local minimum. We also know then that that graph will be concave up. If it's a local minimum, remember it's the lowest point on the graph, so it will be a happy face or concave up. And then if we look at the gradients along that curve, they start as negative gradients, they change to positive gradients, so the gradients are increasing through that curve. On the other hand, if the second derivative of the x value of a stationary point is negative, that stationary point is a local maximum. In other words, the graph is concave down. All right, because if we look at the curve, if it's a local maximum, it's the highest point on the graph. So it will be a sad face or concave down. And then if we look at the gradients of that curve, they start out as positive gradients. Then through the turning point, they change to negative gradients. So the gradient is decreasing through that portion of the curve. Thanks for watching Max Maths. If you liked what you saw, please like, share, and subscribe.